I'm going to wait to see if it's streaming. I'm gonna stay here for 1 hour today. And I'm gonna continue to do the article about proof of stake and proof of work. So I'm gonna start from where it stopped last time. Not sure if I read this.
Mining. Last edit at Corwin Times, January 12, 2023. Proof of work is no longer underlying Ethereum's consensus mechanism, meaning mining has been switched off. What is Ethereum mining? Mining is the process of creating a block of transactions to be added to the Ethereum blockchain in Ethereum's now deprecated proof of work architecture. The word mining originates in the context of the gold analogy for cryptocurrencies. Gold or precious metals are scarce, so are digital tokens, and the only way to increase the total volume in a proof of work system is through mining. Cost of mining. Potential costs of the hardware necessary to build. How Ethereum transactions were mined. The following provides an overview of how transactions were mined in Ethereum proof of work. An analogous description of this process for Ethereum proof of stake can be found here. A user writes and signs a transaction request with the private key of some account. The user broadcasts the transaction request to the entire Ethereum network from some node. Upon hearing about the new transaction request, each node in the Ethereum network adds the request to their local mempool, a list of all transaction requests they've heard about that have not yet been committed to the blockchain in a block. Block. Transaction fees. Verifies the validity of each transaction request, i.e. no one is trying to transfer Ether out of an account they haven't produced a signature for, the request is not malformed, etc. And then executes the code of the request, altering the state of their local copy of the EVM. The miner awards the transaction fee for each such transaction request to their own account. Begins the process of producing the proof of work, certificate of legitimacy, for the potential block, once all transaction requests in the block have been verified and executed on the local EVM copy. Eventually, a miner will finish producing a certificate for a block which includes our specific transaction request. The miner then broadcasts the completed block, which includes the certificate in a checksum of the claimed new EVM state. Other nodes hear about the new block. They verify the certificate, execute all transactions on the block themselves, including the transaction originally broadcasted by our user, and verify that the checksum of their new EVM state after the execution of all transactions matches the checksum of the state claimed by the miner's block. Only then do these nodes append this block to the tail of their blockchain, and accept the new EVM state as the canonical state. Each node removes all transactions in the new block from their local mempool of unfulfilled transaction requests. New nodes joining the network download all blocks in sequence, including the block containing our transaction of interest. They initialize a local EVM copy, which starts as a blank state EVM, and then go through the process of executing every transaction in every block on top of their local EVM copy, verifying state checksums at each block along the way. Every transaction is mined, included in a new block and propagated for the first time.
I think I'm gonna read those through and then search for the source code. I'm not really sure if this code here is the source or not. So if it isn't, I'm gonna search for the source code after reading this through articles here. I think I'll read this one first because it seems like the other one is more important. So I wanna close this tab here first.
Mining algorithms. Last edit at Rex 4539, Prerequisites. Dagger Hashimoto. Dagger Hashimoto was a precursor research algorithm for Ethereum mining that Ethish superseded. It was an amalgamation of two different algorithms, Dagger and Hashimoto. It was only ever a research implementation and was superseded by Ethish by the time Ethereum mainnet launched. Dagger involves the generation of a directed acyclic graph, random slices of which get hashed together. The core principle is that each nonce only requires a small portion of a large total data tree. Recomputing the subtree for each nonce is prohibitive for mining, hence the need to store the tree, but okay for a single nonce's worth of verification. Dagger was designed to be an alternative to existing algorithms like SCRYPT, which are memory hard but difficult to verify when their memory hardness increases to genuinely secure levels. However, Dagger was vulnerable to shared memory hardware acceleration and dropped in favor of other avenues of research. Hashimoto is an algorithm that adds ASIC resistance by being I/O bound, i.e. memory reads are the limiting factor in the mining process. The theory is that RAM is more available than computation. Billions of dollars worth of research have already investigated optimizing RAM for different use cases, which often involve near-random access patterns, hence, random access memory. As a result, existing RAM is likely to be moderately close to optimal for evaluating the algorithm. Hashimoto uses the blockchain as a source of data, simultaneously satisfying 1 and 3 above. Dagger Hashimoto used amended versions of the Dagger and Hashimoto algorithms. The difference between Dagger Hashimoto and Hashimoto is that, instead of using the blockchain as a data source, Dagger Hashimoto uses a custom-generated dataset, which updates based on block data every n blocks. The dataset is generated using the Dagger algorithm, allowing for efficiently calculating a subset specific to every nonce for the light client verification algorithm. The difference between Dagger Hashimoto and Dagger is that, unlike in the original Dagger, the dataset used to query the block is semi-permanent, only being updated at occasional intervals, e.g. once per week. This means that the portion of the effort of generating the dataset is close to zero, so Sergio Lerner's arguments regarding shared memory speedups become negligible. More on Dagger Hashimoto. Ethish. Ethish was the mining algorithm that was actually used on the real Ethereum mainnet under the now deprecated proof-of-work architecture. Ethish was effectively a new name given to a specific version of Dagger Hashimoto after the algorithm got significantly updated, whilst still inheriting the fundamental principles of its predecessor. Ethereum mainnet only ever used Ethish. Dagger Hashimoto was an R&D version of the mining algorithm that was superseded before mining started on Ethereum mainnet. More on Ethish. Further reading. Know of a community resource that helped you? Edit this page and add it.
I may read this stuff here because I don't remember where I stopped. I think I stopped on explaining. Oh no, the mining pool was here. The Ethereum each block of the blockchain contains a block difficulty, mix hash, and unknowns. These values are related to the cryptographic protocol EFHASH, responsible for creating the proof-of-work consensus. Now it's on proof of stake, blah, blah, where miners race to calculate the value of the knowns of each block. The way they do it is by putting a dataset which contains the full chain through a mathematical function that generates a mix hash below a target that is dictated by the block difficulty. Okay, so now I'm gonna read this stuff and I'm gonna see if the code for EFHASH is there or not.
Ethish. Ethish is a modified version of the Dagger Hashimoto algorithm. Ethish proof of work is memory hard, which was thought to make the algorithm ASIC resistant. Ethish ASICs were eventually developed, but GPU mining was still a viable option until proof of work was switched off. Ethish is still used to mine other coins on other non-Ethereum proof of work networks. How does Ethish work? Memory hardness is achieved with a proof of work algorithm that requires choosing subsets of a fixed resource dependent on the nonce and block header. This resource, a few gigabytes in size, is called a DAG. The DAG is changed every 30,000 blocks, a 125-hour window called an epoch, roughly 5.2 days, and takes a while to generate. Since the DAG only depends on block height, it can be pre-generated, but if it's not, the client needs to wait until the end of this process to produce a block. If clients do not pre-generate and cache DAGs ahead of time, the network may experience massive block delay on each epoch transition. Note that the DAG does not need to be generated for verifying the proof of work, essentially allowing for verification with both low CPU and small memory. The general route that the algorithm takes is as follows. There exists a seed which can be computed for each block by scanning through the block headers up until that point. From the seed, one can compute a 16 megabyte pseudo-random cache. Like clients store the cache. From the cache, we can generate a 1 GB dataset, with the property that each item in the dataset depends on only a small number of items from the cache. Full clients and miners store the dataset. The dataset grows linearly with time. Mining involves grabbing random slices of the dataset and hashing them together. Verification can be done with low memory by using the cache to regenerate the specific pieces of the dataset that you need, so you only need to store the cache. The large dataset is updated once every 30,000 blocks, so the vast majority of a miner's effort will be reading the dataset, not making changes to it. Mix 9 hash bytes equals 64 hashtag hash length in bytes 10. The use of SHA-3. Ethereum's development coincided with the development of the SHA-3 standard, and the standard's process made a late change in the padding of the finalized hash algorithm. So that Ethereum's SHA-3256 and SHA-3512 hashes are not standard SHA-3 hashes, but a variant often referred to as Cupcake 256 and Cupcake 512 in other contexts. See discussion, e.g. here, or here. Please keep that in mind as SHA-3 hashes are referred to in the description of the algorithm below. Parameters. The parameters for Ethish's cache and dataset depend on the block number. The cache size and dataset size both grow linearly. However, we always take the highest prime below the linearly growing threshold in order to reduce the risk of accidental regularities leading to cyclic behavior. 1 def get key size, block number 2 SZ equals cache byte init plus cache byte s growth asterisk, block number / epoch length, 3 SZ dash equals hash bytes 4 while not is prime, S.
And so I guess this is the algorithm. I'm just gonna copy the stuff as I read, I think. I'm gonna put all of it on the code there. Trying to think if it's worth changing stuff or not, because if I do it like this, it's gonna be exactly the same as it is on the documentation, which means that it's kind of pointless to do it. But I think I'm only gonna do it like this for now until I do an article that relates all of them. But I'm trying to think if it's worth. Yeah, I think I have to study the algorithm first. So copy the stuff first and then read through the code to see if I have any conclusions about it. And the main priority for me is for doing this article series, to understand how the code works more. So that in the future I can think about different ways that I can implement the same code.
Ethereum's development coincided with the development of the SHA-3 standard, and the standards process made a late change in the padding of the finalized hash algorithm. So that Ethereum's SHA-3256 and SHA-3512 hashes are not standard SHA-3 hashes, but a variant often referred to as Cupcake 256 and Cupcake 512 in other contexts. See discuss. Parameters. The
I am very tired today. I think I didn't sleep well, but I decided to stream just for the consistency of it. But I really don't feel like streaming right now. I think I need to do an article about completeness to study more because it's something that I am very curious about since I've read the article, this stuff about it. I think it's an essential component to the whole blockchain thing. It's pretty much the basis, I think the foundation of the logic behind all the blockchains is the boundary of NP completeness. So understanding the mathematics of this and how people come to the conclusions and build the cryptography, I think is essential. Because I wanna, as always, try as much as possible to break down to first principles so that I can think more about how to use the first principles in different ways. I'm not gonna read through all this stuff. And the thing is that these articles that I'm doing now is just more for give the introduction, let's say, of the consensus algorithms, of understanding how the basic things work. But I wanna use ChatGPT to search for this or for studying the whole source code of Ethereum and other blockchains. Whatever.
The parameters for Ethicia's cache and dataset depend on the block number. The cache size and dataset size both grow linearly. However, we always take the highest prime below the linearly growing threshold in order to reduce the risk of accidental regularities leading to cyclic behavior. 1 def get key size, block number 2 SZ equals cache bytes init plus cache tables of dataset and cache size value, cache generation. Now, we specify the function for producing a cache. 1 def cache size, seed 2n equals cache size / hash bytes 34 hashtag sequentially produce the initial dataset 50 equals SHA-3512, seed, 6 for I in range, 1, n. 7 o.append, SHA-3512, o-1, 89 hashtag use a low-round version of rand memo hash 10 for in range, cache rounds 11 for I in range, and 12v equals oi 0% and 13 oi equals SHA-3512, map, XOR, o, I1 plus n, %n, ov, 1415 return 016 show all copy. The cache production process involves first sequentially filling up 32 megabytes of memory, then performing 2 passes of Sergio Demian Lerner's rand memo hash algorithm from strict memory hard hashing functions, 2014. The output is a set of 500.
Yeah, I need to study this Gakuk, or however you say this stuff here, and Shatri. I want to see how these relate to zero knowledge proofs as well, and KZG commitments. Maybe I should do another folder instead of the blockchain only dedicated to this topic of cryptography. I think that's a good idea. In the same way that machine learning has linear algebra. I think those are the fundamentals probably. Comes down to mathematics at the end of the day, I think. Of linear algebra is to machine learning what cryptography is to blockchain. And I think that I have to find the intersection between the two. So it's probably some mathematical property. I think that the complex plane has something to do with it as well. So the bridge is probably at the complex plane. It might be possible that the bridge between blockchain and artificial intelligence is a multifractal on the complex plane. And the whole issue of NP versus P is also based on that. There are videos that I remember, but they're extremely hard to understand from Triblo One Brown about the Zima or something like that. I forgot the name. But there's also another theorem there that I think it is related, but extremely difficult to understand. But then it's not only knowing that, is also understanding the code as well. So how this stuff translates into the code. Maybe I should be making notes here to know. And that's the thing that I'm struggling now, is to decide like the boundary between the articles of what's kind of stuff I'm gonna explain here, because obviously I wanna study this stuff, but if I leave the article like this, then I might forget it later. So, but at the same time, I don't wanna write down there. Maybe I'll only post these articles after I'm finished with the algorithms ones. Finish doing with ChatGPT. I think it's gonna take me 2 days, 2 more days regardless, because there is like I think 7 left, but or 6 categories left, but I thought that it would be better to just leave for doing 2 extra days instead of trying to do a bunch in one day. Like it's more even, but yeah, by tomorrow I'm definitely gonna finish that. So after I finish that, then maybe I'll focus more on this. I think I will forget the algorithms for a while and then just dive deep into this first. Create the cryptography part and just dive into the blockchain more.
We use an algorithm inspired by the FNV hash in some cases as a non-associative substitute for XOR. Note that we multiply the prime with the full 32-bit input, in contrast with the FNV1 spec which multiplies the prime with 1 byte, octet, in turn. 1 FNV prime equals 0x0100001932 def FNV, V1, V2 for return, V1 asterisk FNV prime, caret V2, %2325 copy.
So I think what I should do is to write down all of this stuff there as a comment, or not as a comment, but before this thing here. And then just leave it like this and don't not post this article until I research all of these things. So I can link as well. Maybe I think I'll mention this on this article at some point. This thing here, the SHA thing, SHA tree, this whatever this is, and the cacat as well. So briefly mention that these algorithms are, these cryptography mechanisms are used there, and then I can create an article for each, I think. I want to have a good idea of what is the space of cryptography. I never studied that, I think. Like, what are the boundaries there, and what is the difference between different mechanisms and how they were found and things like that.
Please note, even the yellow paper specifies FNV as V1 asterisk, FNV prime caret V2. All current implementations consistently use the above definition. Full dataset calculation. Each 64-byte item in the full 1 GB dataset is computed as follows. One def calc dataset, full size. Main loop. Now, we specify the main Hashimoto-like loop, where we aggregate data from the full dataset in order to produce our final value for a particular header and nonce. In the code below, header represents the SHA-3-256 hash of the RLP representation of a truncated block header, that is, of a header excluding the fields mix hash and nonce. Nonce is the 8 bytes of a 64-bit unsigned integer in big endian order. So nonce ::-1 is the 8-byte little endian representation of that value. 1 def x 2930 def Hashimoto.
I'm just a little bit confused about this because I thought that this was for the other algorithm, not for if hash. But maybe it uses the same, but the process is different on the other functions. Don't understand really well.
Now, we specify the main Hashimoto-like loop, where we aggregate data from the full dataset in order to produce our final value for a particular header and nonce. In the code below, header represents the SHA-3-256 hash of the RLP representation of a truncated block header, that is, of a header excluding the fields mix hash and nonce. Nonce is the 8 bytes of a 64-bit unsigned integer in big endian order. So nonce ::1 is the 8-byte little endian representation of that value. Essentially, we maintain a mix 128 bytes wide, and repeatedly sequentially fetch 128 bytes from the full dataset and use the fnv function to combine it with the mix. 128 bytes of sequential access are used so that each round of the algorithm always fetches a full page from RAM, minimizing translation look-aside buffer misses which ASICs would theoretically be able to avoid. If the output of this algorithm is below the desired target, then the nonce is valid. Note that the extra application of SHA-3256 at the end ensures that there exists an intermediate nonce which can be provided to prove that at least a small amount of work was done. This quick outer POW verification can be used for anti-DDoS purposes. It also serves to provide statistical assurance that the result is an unbiased, 256-bit number. Mining. The mining algorithm is defined as follows. 1 def mine, full size, dataset, header, difficulty 2 #0 pad target to compare with hash on the same digit 3 target equals zpad, encoding, 2256 / difficulty, 64, -14 from random import randint 5, defining the seed hash. In order to compute the seed hash that would be used to mine on top of a given block, we use the following algorithm. 1 def get seed hash, block 2s equals, \x00, *323 for I. Note that for smooth mining and verifying, we recommend pre-computing future seed hashes and datasets in a separate thread. Know of a community resource that helped you? The following code should be prep-ended if you are interested in running the above Python spec as code. 1 import SHA-3, copy 23 hashtag assumes little endian bit ordering, same as Intel architectures, 4 def decode int, s5 return int, s::1.encode, hex, 16, if sl067 def encode int, s. 8a equals
Also, zpad is this one. I can remove from here. And maybe what I should do is to create a different project and then import all this stuff and look at the source code. And I'm thinking about going to the GitHub repository from Ethereum and then using ChatGPT to explore that. Also, here's the function, but I still have. Okay, so this is here. I still have to look at the library, so it doesn't matter. I think I'm gonna remove this. And why don't you put some music and then just study this code now? I think I'm gonna study SHA, SHA or SHA-3, however you say this. A lot of interesting stuff here. Not sure if the Go Ethereum is the main thing, the main client. Maybe we should ask ChatGPT. Yeah, so it is the Go Ethereum. So now I have to think about the priorities, which ones I'm gonna do first. Because I have to follow some kind of a logic. There's too many things to study. I think I need to dive deeper into cryptography first. And then I will, yeah, but it's hard to tell. Because I also need to understand because obviously it's not just cryptography, it's more things related. The network and the way that the blocks interact. So EVM is a bigger part, and then from EVM you have the cryptography, which is the fundamental parts that allows EVM to exist and the blockchain to exist. So I'm not really sure. And maybe I should stop what I'm doing there with this article and then focus on the cryptography ones. Not sure if it's worth trying to finish this one now. I think I want to leave it like this, and then I'm gonna focus more on cryptography now. Then I'll go back and finish later. Because once I have a better understanding of how everything works, it's gonna be easier to write as well about the other consensus. I think that's the best approach, probably, is break down into fundamentals, because everything's gonna be a variation of that. It's probably gonna follow the 80-20 rule, where most of the algorithms, the consensus are slight nuances in differences between the hash functions and the way that they are integrated. So probably start with cryptography first, and then I'll look into the EVM implementation. I'm gonna close this one. I wanna look into this as well. Maybe I should fork this. This is the Web3 Python if account abstraction. I wanna study this because I'm curious about account abstraction. I still don't understand it very well, and that's the reason why I wanna study this code here. I better focus on this later. Yeah, ChatGPT is incredibly good for this kind of stuff, I think. A lot better to search for. So I think that's probably what I should be doing now then. Just go to the repositories and then use ChatGPT to help me figure out which ones are more, to understand the general structure of it, and then study the source code to understand more how it works. Close this one. So this is the C++ version. I think this one is the Python version. Maybe I should download these things as well. I should probably create... the thing that is complicated about this stuff is that it's hard to think about a good way to organize this. Because I don't want to leave in the blog post resources, but then if I put here, sometimes it's hard to remember where I put the code. Because I have now I don't have as many, but I have a lot of other stuff on the backup hardware. So it becomes hard to remember where I put each thing. And I end up not using them. So maybe I create something here. I think I'll do... maybe I'll do actually blockchain study and then I'll put the code here. But I'm gonna do this later off stream because I'm gonna open on PyCharm to set up the virtual environment because it's easier. And then I'm gonna copy all of this stuff on that folder. I think I'm gonna study with both ways, but I'm gonna copy because maybe I will implement some of them or like do things with them. I think I'll close this one for now then. Let's study cryptography first. I know this one is used for zero knowledge proofs, is related to it. Or I think it is, I'm pretty sure it is used for zero knowledge proofs. Obviously when I study that as well. This is a very big thing as well, to understand how MetaMask work and other wallets work. I don't really know very well. Like how do they create all the keys and manage all the keys. I know that now they changed, I think it was Consensus or some other, I think Infura and maybe Alchemy as well, that they started collecting the IPs of people. And also because of market dynamics, the wallet provider is going to have a Pareto distribution kind of thing where most people are going to use one, which is MetaMask now. So that's another point that is weak for our blockchains. And I think that this is the main fundamental problem. It's very hard to come up with something that it doesn't rely on the whole infrastructure. Like it's kind of impossible, not impossible, but it's extremely difficult to think about something like that. Because in order to make this whole thing work, you need to make it available on GitHub, and then search engines also have to pick it up, because otherwise how people are going to use it. And then regardless of which way you think about it, it's always going to be centralized to some degree, because the whole infrastructure depends on these points of connection, and that's the biggest problem. But I think like this is the only way to go with things, I think, because if we don't go in this direction, then if it doesn't become a structure of hash functions in the Internet of Things with AI, then I think that is very low probability that the system will continue to work. That's the biggest problem. Like, it's not that it is the best. It's not that it is fully decentralized. It's just that I think it's the only way, the only thing that we can do to maximize our chances of survival in relationship to artificial intelligence, because otherwise, like, I don't see how it doesn't get worse and worse. Because you have more and more power, and then eventually everyone can blow up a nuclear weapon, and then everyone dies. And that's what technology does. It's gonna become more and more powerful if there's no mechanism in the whole infrastructure. Then how is everything gonna work? I don't see how. But then the issue is, how do you... I think it has to be something that is not... It isn't like it goes against the whatever the mainstream is, and it has to be something that is captured by... So, for example, it's not something that wants to take down Google. It's something that Google has to incorporate because it's the better thing to do, if that makes sense. So it has to be something that uses the logic of the Nash equilibrium of the arms race to make people adapt it, but not because they're forced, just because it's the best thing to do. And that way, then I think it makes sense, because then, like, there isn't a point of failure, I think. Because then everyone is incentivized to adopt the whole system, the new system. But maybe that's what Ethereum and other blockchains are supposed to be. Because at the end of the day, if it is proof of stake, then whoever has the most money controls the thing anyway, so... I'm gonna close these ones now and focus only on this stuff here. I'll focus on this later as well. And first cryptography, then maybe the keys and understanding wallet. And then I'll go back to doing the consensus algorithms. I'll look into the Python implementation first, because I'm more familiar with Python, and then I'll look into the C++ and C documentation. Or code after. So this probably only works on Linux, which is a pain in the ass, because then you have to install the virtual machine or use the DevSL. wonder, I think I can put the URL maybe. Obviously, I want to know so it's more effective because everything is connected. There is one file that is gonna be the main one, and that is gonna have the code for all of the other ones. Not all of the other ones, but there's always one file that it makes more sense to start from that file because the code from the file is used on other files, and then so on. And then by going through that flow, it's better to understand the overall structure of the thing instead of starting from the main file and then there's a bunch of code from the other ones and then you kind of get lost, I think. That's the challenge for me, and it has always been the biggest challenge, which is to understand how the connection of the project and which way to go about it that makes the most sense with this flow of learning new things. That's why I did the visualization stuff, which would be helpful, but there is no... And the only difference is a dash. So I think it is referring to this one. But here there isn't any folder, so maybe it's inside of one of these. Yeah, there is no C folder. I think he has the wrong repository. Yeah, he's talking about this one. which is the C implementation. So this algorithm is here as well. I don't know Go, but it doesn't seem like it is that hard to learn because it's probably the same as every other language with small nuances. So it isn't hard to understand what is going on here. So maybe I should ditch this other one and just study this one. Let me think. Let's see if it is capable of giving me if I write it like this. So the other thing is maybe I should watch videos and read some stuff about the algorithm first, the Keka 256, and then I should go into the repository. I think that's what I'm gonna be doing. I'm gonna stop this one and I'm going to... I think I should ask myself what is the fundamentals like between all the blockchains, and then try to study that first. And then after I study that, then I create this other, because these are just going to be consequences of the implementation of the fundamentals. And then I can link people to the fundamentals from these ones. So it makes a lot more sense to build from the ground up and understand the fundamentals first very well, and then do these ones. Because consensus is the fundamental as well, but it is built on top of cryptography, I think. So do cryptography first, and then I'll think about the consensus. Also, it does give me the thing. The C folder which contains... The only thing is that I couldn't find this C folder here. So maybe it's just the wrong response. But what I'm gonna be doing is just that with ChatGPT. Because after it gives me those main files, then I can look at the code and I'm gonna ask questions to ChatGPT to clarify the code. I should also look into the but because that's the thing that is kind of hard, because then if I look for the algorithm for the validating function or for the proof of stake function, then like it becomes hard to draw the line which article to do first. I think I have to think more about it on this question of how to, without doing all the research, how to think about what are the fundamentals between all of the blockchains, because that's what I'm trying to get at, not just Ethereum. How can I study the fundamentals in a way that allows me to understand the most amounts of different protocols at the same time, just by knowing the fundamentals, and then building the articles based on that, and then exploring the other articles by exploring the fundamentals of the nuances of each blockchain. But I think the only way to do that is to maybe watch some videos. But the issue that I have with watching videos is that I know what most videos are going to talk about, and they're going to talk about the basic stuff of what is proof of stake, what is proof of work, that kind of stuff. So I have to think about how to extract the... Maybe I can ask ChatGPT, but then the question, like, what should I ask? That's the thing. What are the fundamental... What are the core cryptography algorithms used on all blockchain protocols? And maybe that's a good question. Nice. Yeah, that's the way, I think. Much better. Because now I can study all of the algorithms first, and then I'll derive all the other stuff after. And this is weird as well. Never seen it do this. Oh, I forgot. It's true. I'm gonna save this one for the other, for cryptography, and then copy all of the... So the question I have is how to capture what's essential, like what are the nuances, or what stays the same on all of them. But I think there isn't gonna be any way to do it like without studying one by one. That's the thing. I think I'm gonna ask ChatGPT, but I'm assuming it's gonna give me a generic answer because I don't know enough to ask good questions about it. And obviously these are not all, but I think that studying these ones are gonna be like I can get another list after I study all of this and I cover the consensus that I have there on the other topic, the other category. So I'm gonna do like this, where for this category here, I always study the consensus of this, the algorithms of this consensus, or these ones first, and then I'll go back and forth between the two. Maybe I'll leave it like this, so I know which one is referring to. It's probably better. Fuck. Whatever. Authority. No. The fuck? I'm thinking about how I'm gonna do this. What is the best way to do it? the way that I'm thinking now is just do like this. The way that I'm gonna do with Ethereum, look for the source code and then use ChatGPT to explore the repository. But I'm thinking more about how I'm gonna structure the article. Because it has, yeah, first I think I have to figure out what is the main fundamental algorithm. Because this is the problem with this thing here. Here it gave me ifrash. Yeah, these ones are, I think, are the names. Ouroboros, I remember watching a lecture about this, and it's a variation of proof of stake from Ethereum, I think. But yeah, I think most of them. Yeah, but this one, proof of importance, it still doesn't give me anything about what is the actual algorithm, I think. Like how do you... And I think that's what I'm gonna have to do, is for each one I study a little bit more until I find what is the actual algorithm that they use. Because the main point of the cryptography ones is to study the algorithm and not the consensus. Break down the algorithm and then on the consensus talk more about general things about it. Like, so the cryptography one is more specific and the other one is more general and talking about the concept. Yeah, that's the problem. Exactly the kind of response that I was expecting, which is just more generic. Because I'm thinking more about the fundamentals from the mathematical perspective, like of what is actually going on this, because each one of them is going to be a hash function or a variation of that, I think. That's what it's kind of hard for me to draw the line now of from which point it is just a consensus, like how is everything integrated, because I think each one of them is going to be different as well. That's why it's hard to think about the best way to go about it first. I guess I don't understand really well how the if hash goes with the context of the whole thing in Ethereum. That's the problem. I guess I know that actually. It's just used based on the history. You have the data set and then data set. You use that to compute the hash. So that's how it's related. Maybe I'm overcomplicating things in my mind of how it works. Because I know there is a lot more to it, because there are a lot more components to the whole thing. Because the other components are about the block building part of the transactions and the way that, like, yeah, that's the thing. I think the other components are also, it's also based on hash functions because of public keys and private keys and the way that the block is built, and the network, I think. So those are the other components that are missing, I think. Is understanding better the network, how it works for each node to send and receive transactions, and in the mempool, and for creating the private keys and the account abstraction. Not account abstraction, the smart contracts. So those are the components, I think. But all of them are gonna be based on. So maybe I should put something on SkyDraw to organize my thoughts, so that I think better on how to do this. Because I assume that most of them are gonna be similar, so what is this one? Be consensus. Yeah, I'm gonna leave this stuff here so I can think about it later. I think those are the 3 pillars, and then each one of them uses hash functions. I have to understand how they are connected. That's the thing. Like at the very start of the blockchain, how does it work? You only have one node and everyone can lie because it's only one node, so it controls everything. How exactly did it start on the very first node? And the consensus. So I guess for each one of these is going to be a different mathematical function, and that's the difference between them. Yeah, that's the thing that I'm trying to understand, is what's the difference? Like, is the difference only in the mathematical function that creates the hash? Because it wouldn't make a lot of sense to me that that's all the difference. But maybe it is. So the question is how by changing the mathematical function of this hash, how can that change the whole consensus thing? And I guess it goes into the whole thing, because if proof of work, it used the whole data set to compute. But then, yeah, I think the problem I have is because I don't have a very good understanding of the other ones, of how the algorithm is. So there isn't gonna be a way to really know until I study each one more. I'm just thinking, I'm gonna stop streaming soon, but I'm thinking about this now because I wanna, maybe I can save a lot of time if I can come up with the right way to think about it, let's say. To phrase the questions and to organize myself so I can know what is gonna be more important to look at first, so I can maybe decrease the amount of things that I'm gonna look into. So let me think about it. And I feel like this is important because it can save me a lot of time. Yeah, because I want to think about this because as I'm studying them as well, I'm gonna have in the back of my mind what is important and what is not when I'm studying them. I have consensus, peer-to-peer, private case. The question I think is, what does it change? What's exactly, what algorithms exactly are the algorithms? I'm not sure if this is phrased correctly, but whatever. That changed the consensus mechanism. Is it just a difference in hash functions? That's the main question, I think. So let's ask this ChatGPT. The question is phrased wrong, but it is along the lines of what I'm thinking about. And what does exactly change the consensus? Is it just the... But I think that's the problem, because it is the three things, I think. But I might be wrong about this. It might be just be the consensus part, not the proof of work or proof of stake. But if you think about it, it's the whole thing, because the whole thing about MEV is the relationship between the block builder and the validators, and the whole... I think that's the key thing here, which is the mempool. That's the most important part, because that's the layer of flow of information from outside the blockchain to the blockchain. Like that, in that bridge, I think that it makes a lot of difference. So, but the problem is, to understand that bridge, you need to understand all of the three components, I think. So I think private and public keys are probably less important than this shoe, because this shoe, like, the only way for you to have this private and public keys is if you have the consensus and peer-to-peer, I think. I think it has to be both. The changed consensus mechanisms are not just different hash functions, where hash functions play an important role in consensus, driven by a combination of algorithms and protocols, including the use of hash functions, digital signatures, and consensus rules. The hash function is used to perform computational puzzle. Is determined by the algorithm that determines which node will validate the next block, as well as the protocol for determining the validator's stake and rewards. The validator is selected based on their stake and random number. This mechanism is determined by the algorithms that determines which delegates are elected. Yeah, this part is the one that I'm struggling to understand. is the connection between the peer-to-peer and the consensus. I think that's what I need to clarify more. Because when it says things like this, that the algorithm determines which delegates are elected, like how does that work exactly on the, because you have this whole hash function, like you have the if hash there on Ethereum, for example, with proof of work, where you get the data set and then you use the data set to calculate the nonce based on the block difficulty with the algorithm there. But how does that relate to the history of the blocks in the first place? Like, how do you have the data set in the first place? If you're using if you have to use the data set to mine, that's the thing that. And then I think it gets complicated because then you get into the uncle blocks thing, where there's always several different blocks simultaneously because everyone has their own different mempool based on the nodes that they are connected to. And then that's what generates that from those pools. Everyone's gonna have different histories of transactions, and then from those transactions, like that's the whole thing that is difficult to understand. How from that part it goes into it becomes the main chain. That's what I need to know. So maybe does it go? The mempool. Yeah. I don't think it's like giving anything interesting, but so the other question is whether or not all of the different consensus algorithms for the protocols imply a different peer-to-peer network thing or not. I assume that the answer is yes, because the consensus is directly connected with the way that the nodes relate to each other. And I think that's where the game theory part comes into play. So the game theory is the peer-to-peer relationship, and the consensus is about cryptography. But the thing is that game theory is not a very good description because it's not gonna allow me to study this, like the fundamental. Yeah, I guess you can study Nash equilibrium based on that, but like it's not really a clear thing because I think that game theory a lot of the times is more abstract than like it's different than it is on poker where you have a clear set of rules and then you can calculate the game theory based on the exploitation and the values of calculating pot odds and equity and that kind of stuff, because that is a lot more clear. But here when you talk about game theory, like how are you gonna reduce that to the numbers, because there is a much bigger macro context that is involved, which makes it, I think, almost impossible to reduce to. You can only become something abstract that you can think about it, but it's very hard to reduce it to numbers. It's cryptography. Yeah, so here I think I'm gonna put the names of, I'm gonna do this later off stream. Put these names here inside of this thing here. And then I need to find the equivalent for the peer-to-peer network. The thing is because there's so many things, it's hard to decide which one to do first. Because now I don't know if it's because then I might be getting too abstract, and it's better to study the consensus first and the cryptography for all of them first, and then study the peer-to-peer. Because then I can do the articles already. But I think it makes more sense to study the mempool and the peer-to-peer network first, because it's the one that are most weakest, the one that I'm the weakest at. I don't understand really well. I kind of understand based on the free code camp thing that I did of the WebSocket connection between nodes. So I kind of have an idea of how it works in my mind, but I never studied the source code to understand how it works. Maybe that I should study that first. The mempool. I think I should study that first. And I think about it because it's like the flow of information of the peer-to-peer determines the that plus the hash function determines the blockchain. So it's like a flow of information from peer-to-peer that is translated into some hash function. So the hash function works like a gate, and it's one of the, I forgot the name in English, but a good analogy to the thing that creates energy out of water. Like that, you have the water flowing, and then you have the bridge, which is the hash function, and the water is the information between the nodes traveling around, and then the bridge is the hash function, which is done, and then that's where it's gonna vary, like how the mechanism of the thing works. Proof of work is through the energy of computation of the GPUs doing calculations. Proof of stake is based on the stake of each node, and that changes the structure of the transactions inside of the blockchain, because that structure determines the transactions, which determines the price and the whole economic thing of the coin or the protocol. I think I'm gonna stop here. I have to finish all of the other stuff. Probably gonna finish tomorrow that thing, but and then now I'm not really sure. I have to think more about this. I could spend more time uh, to understand what I need to focus on first. Because now I'm thinking about that is probably not the best way to study the cryptography first. Yeah, because it is not that difficult as well to understand the cryptography for me. Like there isn't, because the notion of hash function is very easy to understand. I think you just use an input and then you create something from that input, and then the whole irreversible thing like is not. Obviously, the more in-depth way to look at it, is hard, and I'm interested on trying to understand that more, which is the whole NP incompleteness thing, or NP complete. That you have this gap between like these functions where it becomes it's easy to verify but impossible to reverse the thing. That is obviously interesting, but to understand I think it's gonna be easier to understand the nuances of the algorithms themselves that create this thing. Obviously, the mathematics is gonna be hard, but actually think because the hard part about the mathematics is not the actual use case, is more thinking about the broad perspective, what implications, like what are the assumptions and implications of using this method when it comes to the whole context of mathematics itself and the logics of and all of the stuff that is connected to that. That's a lot harder, but the actual use case I think is relatively easy to understand, like the way that it works. For example, in zero knowledge proofs with the directed acyclic graph and the whole polynomial thing where it generates a bunch of things and the whole data availability sampling kind of thing. I don't think that is going to be that hard for me to understand. But the thing that is not very clear is the peer-to-peer network. So that's what it is making me think that it's probably better to. But then how do I classify that? Because the issue with the peer-to-peer is that I'm not sure if it's going to change too much from network to network. Yeah, but that's probably the stuff that I need to clarify first. So I think I'm gonna create another category here, another folder. And I'm going to start with that topic first. But in order to understand how I can structure it, I'm gonna have to it's kind of hard to come up with a name that it makes sense for a category as well. Maybe like this. Because with Ethereum I spend a lot of time reading about stuff about the mempool and thinking about this kind of thing. But with the other ones I don't have any idea if it is relatively the same or not. And even if with Ethereum I don't really know really well how it worked in the beginning of when you have just a few nodes, and how the under the hood process work, like how are the messages working between nodes, from node to node. That's the stuff that I need to clarify first. And then I have to look into the other chains as well to see if it's similar or not. And I think that is gonna make it easier to understand the hash functions as well. So it's probably better to start from peer-to-peer, which means that I'm not gonna do this stuff here next time. Let me see. And the issue is I know that it gets very complex, especially now because of the whole proposer builder separation kind of
The mystery
thing.
of life isn't a problem to solve,
Like, my main concern is that
but a reality to
it should make it
experience.
more efficient for me to study everything, so I don't waste a bunch of time like looking at stuff that doesn't matter that much. That's why I'm spending a lot of time now thinking about this. And so it's on the Go Ethereum. And the Go Ethereum is massive. So it's both this thing and the Lighthouse code that I wanted to study as well. Like how to build the... Maybe that's what I should be doing actually. To build my own node again. Go through that process again and study the source code of the connection there. To understand more how it works. But the thing that I want to think about is more from the standpoint of not focusing too much on Ethereum, but focusing on the fundamentals. That's the stuff. Like I guess that's my concern is like, because obviously I can study, because I know how deep it's gonna go if I study the whole, because it goes into MEV and then it goes to a bunch of different things that you can do on the blockchain to like change or manipulate the mempool. And then it gets very deep. That's the problem, because I don't want to get too much into the specifics of Ethereum itself, but understand more the fundamentals of the way that the connection works between the peer-to-peer relationship, the mempool, and how that translates into the consensus algorithm. Oh, it's here. Oh. So maybe a good question to ask is if all of them have a mempool, which it makes sense that they will have, because otherwise how are you gonna put the transactions in the blockchain? It doesn't make sense. You need to have a layer that is for validating on whether or not transactions are good, and that layer is gonna be, the consensus algorithm is gonna be related to that layer. So it's both the peer-to-peer flow and then the consensus algorithm that determines whether or not the transactions are inserted into the system. And I guess that's where the whole caching thing comes, which is kind of hard to understand. But it's like yeah, because how are different nodes updating their blocks? That's the thing. I guess you always have that's the stuff. You always have the whole data set with the transactions, and then but the problem is because you can have multiple different mempools and multiple different histories. So like let's say I'm a miner and I'm trying to figure out if the transactions are gonna go there or not. I guess I need to have two separate data sets, one that contains the history, the actual history. Yeah, but that's the thing. The other data sets, because I'm also trying to validate the transactions at the same time that I should be receiving the valid. Yeah, that's the mechanism that is hard to understand. Because if I'm a miner and then I'm doing the calculation to validate the transactions that I'm receiving, but at the same time there's someone else that is doing the calculation, and let's say they ring, let's say they figure out which ones are true or not. Then if they figure out before me how, because I still have all the transactions that I'm still calculating, so they're gonna propagate the validated ones that they were able to compute to me, but at the same time I'm still calculating the other ones. So how does that work? Like, I guess that's where the peer-to-peer comes into play, I think, because the moment you receive the validation or the message that one of the nodes on your network, on your local network, was able to validate, to compute, then you need to do some other form of computation. Instead of continuing to try to validate your transactions, you need to drop that and then validate them to see if they actually did the correct computation or not. Like, and then after you do that, then the dataset gets updated. That's the whole thing that is confusing, I think, to me. I need to clarify more. And I'm contemplating whether or not, because I was thinking more about running the node again later, but maybe I should be doing that now on this folder here. Yeah, I was gonna run it here, I think. Because I know that this will probably take time. But maybe not, actually. Yeah, I have all the commands that I used the previous time. Because the thing is not that hard to run the node itself, it's pretty simple. But what is gonna take time is to understand the source code from Lighthouse and GIF. But I think I should be doing that now, probably. So maybe next time if I don't solve this off-stream, because off-stream I'm gonna be focused more on creating the blogs with ChatGPT, the articles, until I finish all of the algorithm ones. But if I don't run the nodes on off-stream, then I'm probably gonna do this tomorrow. Of running this again my own node, and then as I run the node and start getting the validations, I study the peer-to-peer network, and then I'll do the articles about that first, and then I'll dive again into the consensus. I think that's a better strategy. And the whole thing is that I don't remember about this secret here, JWT. And I think the thing is I'm not gonna study MEV boost now, I think. Or any particular thing about the Ethereum blockchain. I wanna stay more focused on the fundamentals. Yeah, run this first. I'll probably run it from inside of this thing here. So I'm gonna stop here. I'm gonna go do the algorithms thing. I'll probably come back tomorrow, and if I haven't done if I haven't started the node off stream, then I'm probably gonna do that tomorrow, and start doing research with ChatGPT. Go over the source codes to understand how the peer-to-peer works.